Now called to order. I am Commissioner Pinocci, presiding officer for this public meeting. With me today is Vice Chairman Johnson, Commissioner Fielder. I'm hoping that Commissioner O'Donnell may dial in later and perhaps we'll get Chairman Brown to join us. The time is 1:30. The date is June 29th, 2021, and we are located in the Bollinger Room of the Commission offices in Helena, Montana. The purpose of this meeting will be to listen to a presentation by Dave Townley and Jeff Townsend on behalf of CTC Global regarding the development and performance of modern advanced conductors and CTC Global position on the benefits of advanced conductors to the Montana electric consumer. CTC intends to also include a proposal for Montana transmission and distribution efficiency policy. Northwest Energy also intends to make general comment at the conclusion of CTC's presentation and has made information available on this topic. That material should be located at the entrance to the Bollinger Room. This meeting is not the topic of any currently pending contested case before the commission, and the commission does not anticipate taking any official action as a result of this meeting. Rather, this is strictly an informational meeting. Following the presentation, CTC Global has offered to answer questions raised by the presentation by commissioners and members of the public. During that time, people wishing to make general public comment may do so as well. The commission now invites CTC Global to proceed with its presentation. Mr. Townley, the floor is yours.
Very good. Thank you. Okay. All right. We should be able to pick that up with the webinar now. Up one. Yeah, perfect. Okay. Very good. Thank you again. I preface, had an opportunity to meet Commissioner Pinocci about a year ago, and we've been working together since that time. He's been giving a number of presentations around the state about the technology, but we wanted to very much focus on the policy piece of the technology as well as the technology itself. And I've had the opportunity to meet Commissioner Johnson for about 4 times over the last 2 years. So good conversations there as well. We've worked with the Minnesota PUC, and we'll refer to that. We've also worked with the 14 state commissioners who are part of OPSI, the organization for the PJM states organization, and talked to them much about the same sort of technology and application, and continuing to pick up some discussions with particular states right now. So with that preface, would like to tell you a little bit. We think there is an opportunity here that we want to highlight to you, educate you on. We'll do that by way of going through some background. We'll describe the particular brand that we have. You have a sample in front of you, the ACCC Conductor. We'll talk just briefly about the power line history, how we got here, and you'll see the theme coming through very much so. Some attributes, uses, benefits. We'll mention some project examples, a couple slides just on CTC, and then we'd like to talk about the proposal for transmission and distribution energy efficiency policy for Montana and what that does. So a comparison, and you have one sample of that, but as in the picture and here, the ACSR is by far the most widely used conductor in the US today. Became the standard pretty much after World War II, and we'll comment on that in a minute. But you see it's steel reinforced, just wire, and most of the strength comes from the wire. The aluminum is an alloy, and that's the current carrier. So together, this makes up the most common conductor that you'll see in the US. This conductor replaced the steel with carbon fiber, a composite. It's smaller, but stronger than the steel it replaces. It has very low expansion. So as it, yes.
Technical difficulties. Nobody can see the presentation on our stream, so we're going to fix that just for 1 minute here.
Okay, sure.
Entirely your call. This will only take a second.
So how,
Right. Yes, the entire presentation was audible, just the visual component.
Okay. Okay, good.
Yeah, I would encourage you to start again on visual.
They see, okay. Yeah, there's just the one. So yeah, we'll start there. Okay, we're now screen sharing, right? So
Yes.
they can see?
Yep.
Okay. Thank you. And we think the audio was okay. So the introductions and the connections to the commissioners in the past, we'll move on to the discussion. And there was just a listing of the comments that I made about how we wanted to proceed and the kind of background we would give, the technical background, some attributes of the technology, but then move to the energy policy statement itself and why that's important, and give you some values about why it matters to Montana. And so in this, we were describing the classical, most commonly installed conductor, the ACSR, aluminum conductor, steel reinforced. And we were describing that as being the steel core with round wire that carries the electricity. Began to describe then the conductor that is the carbon composite core. We replaced the steel. It's lighter, stronger, and as you heat it up, as you put current through these lines, they heat up, and steel will expand. And if you've attached it to 2 points, like in a tower, then it's going to sag. And here, this will heat up. It will sag, but tremendously less. In fact, called a low sag conductor. This has, because it was lighter in the center, and we're able to use the trapezoid wire, we get more aluminum in the same diameter. So for the same diameter, it turned out to be the same weight. And that gave us some very unique opportunities as well. And we'll talk about reconductoring by literally just changing the wire that's up there with the wire that's an advanced conductor, ACCC, that gives you more capacity, immediately better loss reductions, more efficiency, and 2 times the capacity. You can put twice the power flow through here as you could with this and still not sag out of service. And there's a brief example here that talks about the ACSR traditional and the ACCC both operating at 180C. You wouldn't operate the ACSR there, you can see, because it would sag lower than its clearances are allowed, right? And we'll comment on the operation of that in just a moment. So the value proposition for the advanced conductor, the ACCC advanced conductor, is the capacity. You can put 2 times the flow through here and stay in service. May not design it for that, but you can call on that and get that service out of this conductor. For new lines, it also means that you can have shorter towers or towers that are further apart. That becomes part of the equation in the use of advanced conductors if you want to include that in the design. The efficiency, because you've got more aluminum and it is a annealed aluminum, it is more conductive, then this resistance is lower. The efficiency of this is higher than the ACSR. In fact, it is 25 to 40%, depending on the application and how hard that line is being run. You can get substantial reductions in efficiency, substantial reductions in resistance, a great increase in efficiency. And that translates directly into energy savings. And future proofing is something we hear in a number of applications in some of the markets of the world. We'll touch on that. But by putting this up and getting the benefit of that over power, you can draw more power. You've got energy savings and carbon reduction potential immediately available, but it's cheap insurance for planning model risks, under forecasting in some markets. It's not something we've experienced in a decade or so. We've been seeing a different kind of risk, but that allows you to change the flow on the network, something you may not have planned for, or an upset in the network, and still be able to continue to operate because you can put 2 times the flow through these lines and they'll stay in service. So why does a utility take a look at this advanced conductor? And what we see generally are 3 reasons. First off, they're standard. What they've always been using for one reason or another just doesn't work. The sag, they can't get the right clearance. Ice load is too heavy. Narrow right-of-way, and they need to upgrade the right-of-way. They need to upgrade the power line down that right-of-way, and they just can't do it with their standard conductor. Those are some reasons why they may consider, so what else do I have? What other choice do I have? We also are seeing if it's a lower first cost. Just the initial cost is lower. And that's the case in one of these unique applications where you can actually change and reconductor wire for wire on the existing structure. That's unique because of the weight and the size aluminum that you have versus what you're taking down. But it also means if you need that capacity, that's the least expensive way to get it. You don't have to rebuild the towers. That's a lower first cost. And so we see some that move to this for that application. And then we see cost benefit. And we see that more so in South Asia, Southeast Asia than we do even in the US, where in those markets, we're able to see the bankers and the utilities take a look at a life cycle cost, the full set of benefits and costs that they're reaping, and that the net value is high, and they're willing to move ahead with an advanced conductor versus the traditional solutions that they had. And a quick example in the US, just to illustrate a little bit about what we mean. So this was a New York project, a new line, relatively short, 57 miles, high voltage, 345, 2-circuit, 2-bundle. It's a $440 million project using using an aluminum conductor, steel supported, ACSS. They decided to take a look at, okay, what if we keep the towers the same? We keep all this the same as we had before, but we're just going to take the wire and exchange it for a ACCC ULS of the same size. Drake happens to be the size of the conductor. Well, it costs more. It was about $7.4 million more, 2% of the project cost increase. But just the line loss savings alone, $4 million a year, less than a 2-year payback. And in New York, they say, when you're doing these calculations, use 45 years and a 5% discount rate to give us what that net value is going to be. And that's a $72 million value just on the line loss savings alone over the life of that unit. There's avoided generation capacity and there's CO2 reductions, almost 17,000 metric tons per year of CO2 that were reduced. And that's in New York, which already has a lower emission rate. So by far, the line loss savings there more than paid for that. And in fact, a 12-to-1 benefit cost ratio. And it raises the point for commissioners is, and we've raised this point with the FERC as well, and that is if you're looking at just and reasonable rates, to take the lowest cost may not be the just and reasonable rate when you're leaving this kind of benefit on the table for consumers and the environment. That needs to be considered. I want to quickly take a look at just an overview of the evolution. You'll see a theme that emerges here, but copper conductor, when this industry began 150-ish years ago, copper was it, right? But World War I, copper was taken off the market, used in the war effort, and they had to get a different solution. And they moved to aluminum. Wasn't as conductive, but they could use it nonetheless. And it was relatively weak, though. They had to put a lot of structures close together because it wouldn't support itself very well. So obviously they wanted to stretch it out, get towers further apart. And so they went to an alloy that gave them a little more strength, but they gave up some efficiency, some resistance. Okay. Particularly good in and around metro areas. But by the time World War II came along, following the growth rate after World War II, the ACSR became the standard go-to. That was the product that allowed good overall strength. They could go quite a ways between towers and had good conductivity, but they did have the sag limits that they had to face. About 1970, they came up with the first of what we would call advanced conductors or low sag conductors. When they did the ACSS, a steel supported structure, it let them get more aluminum on there if they wanted to put a trapezoid type wire the way we do. And it was a bit stronger, but the alloys they used, they were able to run them hotter. And you'll see that in the next slide. But that did bring us up to the advanced conductors that are constantly looking at how do we get stronger strength and still maintain good efficiency. I'm going to spend a minute or two on this one to learn a couple of things coming out of this particular slide to learn. This was done by Hydro One. This is a large Canadian utility in Eastern Canada. And they were doing 65 meter span. So this was just a test. And they were just looking at temperature and sag. So this is what they were looking at: conventional and some of these new advanced conductors as of 10 years ago. And a few things I want to point out on here. And you can see the red with the red circle, that's the traditional ACSR. And you see that's the lowest, steepest sag. In all of these cases, they're running them out. The last points out there are 1600 amps. So we don't know what the in-between points, they were just measuring temperature and sag. But at the end, we know that they all are operating at 1600 amps. So a couple of things. Looking down at the circle where I've drawn 100, that's a little hotter than the utility actually would run an ACSR. They start annealing at a little over 90. So normally they'll operate about 75 C, 90 C, maybe 100 emergency. So I picked 100 because I got the data point there. And relatively speaking, this sag is 40 inches across 65 meters. When we're talking about a tower, of course, we're talking about many tens of meters or many tens of feet of sag that's going to be on a tower at 100 C. And you can see, certainly as it ran on out, you wouldn't run that ACSR at those higher temperatures because the tower is not tall enough. That point is what determines if I'm going to use an ACSR and I'm going to run it at 100, I know it's sag. I've got to have a clearance and a safety, and voila, that's the height of my tower. And those are the heights of the towers that you see around designed with those kinds of constraints. The point I want to show here is that even as these advanced conductors, including ACSS, before they get out to their full amperage, before they get to 1500 at the endpoint, they already have sagged enough that were they on the same tower, they couldn't continue to operate. You had to stop because they now would be violating their clearances to the ground, except for two. There are two conductors that Hydro One said, okay, they're well up in there, even all the way out to their endpoints. They still don't sag down low enough. Those are truly low sag that can operate all the way up to their full amperage, which in those cases at the endpoints is about 2 times the power flow or the current flow as the ACSR had at 90C or 100C. The other point I want to show in this slide, the last point, is we commented that all of those endpoints are operating at the same current. We're going to call that current I, because the engineers call it I squared R. That's the heating that goes on in those lines when current flows through them. At the endpoint, they all have the same I. They all are operating at 1600 amps. 1600 square is the same number for all of them. So they all differ only by resistance. If they run hotter, it just means that their resistance is higher in order to run out to that 1600 amps. And here you see the lowest temperature of all of those is the ACCC running at 180, the most efficient conductor of those that were sampled by Hydro One. On this slide, I only want to show that in addition to the base product, the ACCC, and there are 31 different sizes in the US, another 40 different sizes in the international market. So it's quite a range of sizes for the product, but then there are stronger, sturdier products beyond the base. So if you've got ice loading, particularly long spans, extra long spans, or heavy ice loading, you would move to the right. For Montana, we believe, at least what we've seen, and we'd like to work with the utilities to see if this is any different, but we think most of those will be served by this ULS, and certainly by the time you get to the third product there, most all the applications for heavy ice in Montana should be able to be served up through those three products. If you need even more and even extreme, you can move on to the last product there. Could you give us a down and see? There we go. Thanks. Sorry. This ACCC was the very first conductor and currently the only conductor that has been third-party certified as reducing CO2, mostly because it's just more efficient, reduces energy, and the energy related to that CO2. So across 5 scenarios, they tested it and confirmed from 27 to 31% lower carbon emissions as a result of using this in place of the very same diameter and weight ACSR. Here, I just want to give you a sense of around the world, the installation maps. There's over 100,000 kilometers or over 63,000 miles that have currently been installed. Here we're indicating about 59 active, that ranges 55 to 60 a month that are active. In fact, I just got a report today. We energized 11 projects in the last 30 days. We had 58 that are active, and we have 64 that are in scheduling, have been sold, but they're now working with the manufacturers to get onto the production line and the hardware lines. You can see by far most are in South Asia, Southeast Asia, rapidly growing areas, and they recognize the benefits of using the advanced conductors versus the traditional. And the bankers understand that as well as the utilities do. In North America, just stating what's on the slide there, though, a little over 150 projects and almost 11,000 kilometers. In the next slide here, I just want to show a sampling of the kinds of applications, somewhat in the order of greatest expectation or greatest numbers that have been done to the least numbers. The upper left, reconductoring by far is the most widely used application, again, because it's immediately the lowest cost way to get more capacity, you get more efficiency. And here, this picture just happens to be from an AEP project in Texas, and we'll comment on that one in just a minute. River crossings and long spans kind of in the middle there, those were the specialty applications. This was seen as low sag. And so if I'm going across a long span between towers across rivers or mountaintop to mountaintop, that was sort of the first, gee, I need a different solution. And let's use this low sag conductor. Marine and corrosion environments. We saw it in the Texas application, but this steel near the ocean it corrodes, whereas the carbon does not. And so you get that corrosion resistance. Connecting up lots of renewable energy, large amounts of wind and solar. In the second row on the right in the middle, extra high voltage. That happens to be a 500 kV line in China. You see the Great Wall of China, a piece of it there in the foreground. HVDC. We've done 1,000 kV HVDC project. In the middle, new lines, and increasingly the number of new lines. This happens to be Bangladesh, 400 kilovolts. And then in Russia at the bottom right, heavy ice loading represented there. I want to tell you a little bit about this AEP project. They had 240 circuit miles. It was a high voltage 345 double circuit. They were replacing 1,440 miles of the traditional conductor with ACCC. They started with the traditional. They looked at how do I rebuild the towers so that I can put two or a bigger traditional up. But they found that just taking the outage, the amount of purchase power they had to get to cover the time to take the outage and rebuild, they said, no, this just isn't going to work. And ERCOT told them, this isn't going to work. We're not going to let you stay out that long. So they decided that they would use the existing towers. They would put ACCC up instead. And so as not to take an outage, they used a company that did live line reconductoring. So they literally handled high voltage, brought a line down, put it on a pole next to the towers, put new line in, and electrically cut it over, and then repeat the process. And they did that in 9 segments. They ended, and we see a lot of different numbers, but something on the order of $150 million savings and 8 months ahead of schedule. They brought that online. It was only after the fact, though, that they realized, gosh, I'm saving line losses. That wasn't part of their equation, wasn't part of their savings, wasn't part of their choice. It was capacity that they needed and how they were going to get it. But when they took a look at it, they said, I've got line loss reductions of 30%, and that's about $15 million a year for my customers. Wasn't even in the equation. They cut almost 200,000 metric tons of carbon from the Texas emission rates. Wasn't even part of the solution. About 34,000 cars off the road equivalent. They freed up 34 megawatts of capacity, 24/7, 8,760 hours a year, 34 megawatts operating just to get lost in heating the air on the way to the consumer. And they saved water, about 3.5 billion gallons that didn't have to be taken out of groundwater or river water, cleaned up, put in a steam plant, and then lost from steam and out hot water back out into the rivers. And this was one case I just want to mention, again, Southeast Asia. The Asian Development Bank, working with Bangladesh, realized that this ACCC conductor saves energy, saves carbon. I can measure the carbon I'm saving. This is a climate mitigation tool, and that's how they wrote it up in their report. But because they could measure it, they sold it. So here they were estimating almost 175,000 tons of carbon dioxide a year. They sold to Japan, who reports it under their Kyoto report. This is savings that they had. In exchange, they gave a grant to the project. They bought the carbon rights basically out of that. And World Bank is doing that, African Development Bank. They're recognizing this climate mitigation opportunity, this greenhouse gas reduction that actually is taking place because of the savings. But they also are using the terms future-proofing. And future-proofing to them means what I mentioned earlier, the load growths are so high in these areas that they know even if they don't get the transmission system to keep up, they can still run it in overload while they're catching up and not have to take outages. One of those funny things, once you've got electricity, you want it and you want to keep it coming. I want to just have two slides on CTC. CTC is headquartered, it's a US company headquartered in Irvine, California. We have provided for more than $6 billion worth of transmission access assets that have been upgraded, expanded to date. We estimate about 15 million metric tons of CO2 has been avoided, roughly at a rate of about 3 million a year currently, metric tons per year, just by the use of our product. Over 900 projects, 250 utilities in 60 countries. And again, authorized manufacturing partners. That's our go-to. That's how we get into these markets. We invented the technology, we create the core, but we don't sell into these markets. It's a partner who has been working with the local utilities for decades. It's a new product that they bring into their portfolio, and they finish the product. They take our core, they put the aluminum on it to meet whatever the utility was wanting. In the US, there are 3 companies that serve the US. So any of the utilities could get 3, today could get 3 quotes. There's nothing that constrains us as to how many partners we can have. Quick picture of our facilities in Irvine. Upper left is our administration facilities and the production. To the right top, you see those are machines. Each of those machines, if you look closely, each one of them is running 3 cores, 3 lines coming out of there and onto the spools. Machining center, we have a research center, and our shipping processes. I thought you might be interested to see what we've done in the US. So as of a month and a half ago or so, in the US, 143 projects, a little over 6,000 miles installed. Nevada, California, Florida, Texas, those are have been the large users of the ACCC conductor. We're seeing a lot of interest right now in the Northeast. They've got offshore wind coming on, and they already have constrained north-south lines and now having well overloaded east-west lines. So we're working with a number of utilities in some of the eastern corridor states there right now. For the last point, I'd like to just raise the idea with you of this policy. So we've talked a little bit about the technology, advanced conductors, but here's an ask for you to consider. T&D, transmission and distribution project efficiency improvement, should be a design criteria for every transmission or distribution capital project, and it is not today. The criteria often are ground clearance, N-1 contingency for reliability purposes. Maybe I need more capacity. So those are the kinds of things that have driven it for 100 years, and rightfully so. But the thing that is often overlooked in the design process is, can I now make an incremental change to that design and investment and get better efficiency? Because that efficiency, if I can make the right choice that pays for itself, then my customers, my environment, my utility has much to gain for many years, decades into the future. Here I list 4 ways that you can actually increase the efficiency of the T&D or reduce the T&D losses. You can change the way the grid is operated, particularly during the peak period. You can change voltages even. There's several utilities that are testing ways to change the losses during the very highest peak time. You can increase transformer and other substation equipment efficiency. You can change the way the lines run. This happens to be an AEP proposed new tower system that just by the structure on the tower reduces the losses. And finally, I list high performance conductors or high efficiency conductors. And in Minnesota, we'll touch on them just briefly, but they looked at the way the grid is operated, transformer changes, and high performance conductors. They did a 30-year study, a 20-year study, and they found a 30% reduction in the line losses. About 25% was due to the way they changed operating the grid during the peak period. About 25% was transformer improvements. But the surprise to them was half of that benefit came from utilizing advanced high performance, high efficiency conductors. So how might it work? How might it work in Montana? So the policy might say, at the design stage of every transmission or distribution capital project, make energy efficiency improvement a criterion, one of the design criteria, and consider those benefits along with the cost. In other words, a life cycle view. What should be the criteria for that investment? You could say, well, it's going to be a simple payback of X years. It's going to be a net present value of greater than 0, whatever that is. Or it could be what Minnesota did, which was to say, look, we spent decades developing the same tools, tests, guidance for the end use side. Let's take those same tools and tests and apply them to the transmission and distribution investment. So the planners will learn from the end use planners. That's how they did it. That's certainly one way. So method certainly is to open a docket, much like we're doing here, providing information into a docket that gives you the evidence, the support to craft the policy, but that policy really making the efficiency improvement part of a project design process. Now it becomes automatic. The utility will be doing that as a process. And I would comment that today in our process, if the utility were to look at they were doing a project and they said, you know, I meet my design criteria for capacity, but if I just made the wire one size bigger, it's going to cost me X more dollars, but my efficiency gain, my line losses pay for it in 2 years. It's the right thing to do. I'm going to make the upgrade and I'm going to bring it to the commission for reimbursement. But in our process today, and you know, we don't talk about efficiency. We talk about capacity. And the first thing you would hear is the accusing finger saying, there you go again, Mr. Utility, gold plating your project. You didn't need that extra capacity. That's just the process we live in today. But if they have a process description that says, if you've gone through this process, you've applied these tools, and that's the right decision, that means the consumer is winning, the environment is winning, the grid is winning. It's the right choice. So it's a no regrets policy. It really is. It's just the right thing to do. So I want to just mention some some numbers for Montana. So Minnesota took a bottom-up view, talked to their utilities, and they said, we can over a 20-year period, we can do better than a 30% reduction in our T&D losses using those three things that they looked at. What would that mean for Montana? And I'm using the Energy Information Administration, this year's version, January 2021. 2019 is the latest full year that they report out. So I'm reporting 2019 numbers here. 30% reduction, when you gain that in Montana, almost 250,000 megawatt hours per year that aren't just being lost to heating the air. It's like powering 23,000 more houses without producing any more generation. And that's like $10 million a year savings to the Montana electric consumer. That's at 4 cents a kilowatt hour, $40 a megawatt hour, a wholesale rate, not a retail rate. And you would take about 146,000 metric tons of CO2 per year out of emission because you didn't have to generate for the losses that just got burned up in the wires. And about 3 billion gallons of water that wouldn't have to be pulled out of the ground, out of the rivers, cleaned up, just to be put back into the air or in the rivers hot. And it also means about 71 megawatts of wind or solar wouldn't have to be built to still serve the same load with the same reliability, because it's that amount of generation that is just burning up in the air today at a 30% reduction. So some closing thoughts. Advanced conductors should be considered. We think we have the best advanced conductor. That's fine. The utilities can decide whether this is a good one or that one's a good one, and I need this for that project and this for another project. But it's the added capacity of this class of advanced conductors that they can draw on, both for operating capacity as well as some flexible capacity that they can use in disturbances, unexpected load flow changes, or other uses. Reduce thermal sag, and this we're seeing in Southern California. Because the sag is so much lower, they stay up out of the fire zone. And that's a resilience issue. They don't sag down into the zone. They don't get heated up and become part of the problem, but they also are ready to return to service without being annealed or overheated and have to be replaced. They now provide a resilience and a reliability benefit to you. It's greater strength. That core is stronger, both for reliability and resilience. Resistance to corrosion. Reduce capital costs. Certainly, when you're needing capacity and you can put this on the existing structures, it's the lowest cost solution for capacity. And the improved efficiency. As soon as you put it up on a per diameter basis, on the size for size comparison, you're going to pick up 30%, 25 to 40% more efficiency. Reduce line losses and all that goes with that: generation requirement reduction, emissions reduction, and water consumption. So I'm pointing out too that first costs are very important, but they're not the most important. You really need to consider the overall value of the project, the benefits and the costs when considering these long life T&D investments. We believe that implementing a T&D efficiency policy is good for the consumer, the utility, and the environment in Montana. We encourage you to pursue this, and we'll be happy to help with our resources, work with your utilities and your own staff. So for Q&A, what would you like to know? Anything else, any questions that we've raised? We certainly in follow-up can provide our conductor comparison program and analysis, analytical work for any kind of special applications you'd like to consider. What would you like to know? What would you like for us to have a look at with you?
Well, thank you, Mr. Townley, for a wonderful presentation. I do want to mention a couple things. You and I have been working on this for over 2 years. I have been attempting to have this meeting for over a year. The reason it has been delayed is due to COVID-19 restrictions over a year.
Yep.
I committed to ETIC to adopting this T&D efficiency policy, and I have high hopes that the other commissioners will vote in favor of that. I plan to put Lucas Hamilton as my point guy working on this project if he'll take it on, and wanted to set that up. I'd like to ask Northwest Energy, before commissioners ask questions in the public, would you like to go next? Or would you like to wait till after questions?
Commissioner Croce, I think an opportunity to go next would be good.
Okay, please come to the microphone, and the floor is yours.
Can we come up to this table? Or
Whichever you'd like.
that's not the folks here with me that I'd like to introduce.
Okay, please do so.
First of all,
It's on.
I've got these channel. If you want to. All right.
All right. Can you hear me okay? All right. Well, thank you, Commissioner Pinocci, Commissioner Johnson, and Commissioner Fielder. It's actually nice to be in the Bollinger Room after more than a year of isolation. So thank you for the invitation to speak today. I'm Mike Cashel. I'm the Vice President of Transmission with Northwestern. And I have two gentlemen here with me today that are deeply involved in the type of things that the folks from CTC Global just talked about. This is Tom Pankratz. He's our Director of Transmission Engineering, Planning, and Project Management. And then Eddie is our Manager of Transmission Engineering and Construction. So the right guys to talk about this topic for sure. So first of all, I'd like to say a few things. Thank the CTC Global folks for a really good presentation. I don't think there's anything in there that we would disagree with. I think we would like to explain our system a little bit, the constraints on our system. You know, we've got a system that was developed over 100 years. We're talking about the 1900s for parts of our transmission system, not to suggest they haven't been upgraded, because they have, but we have an existing system with which we have to work with. Talk a little bit about the conductors on our system, the use of traditional conductors, and the use of advanced conductors, our conclusions about advanced conductors, and then what we see in the future for our system as well. I wouldn't disagree with the statement that conductors ought to be considered and advanced conductors considered in any of our designs. And I think that both Tom and Eddie would explain to you that they are. It's just that the decisions around those conductors and use of them are complicated, especially in an existing system. And I think you'll find that we've already made the determination that, and we have used advanced conductors, and the type of conductor that CTC Global is talking about probably does have an application on our system in future use, that type of conductor. So we did send along a couple of attachments. They were emailed over to the commission. They put those in front of each of the commissioners. One is basically kind of the history of advanced conductors on our system. And then the second is some actual installations of the advanced conductors. And much of what I've got on these few pages, you've heard already. An advanced conductor, what is it? It's a high temperature, low sag conductor. It allows the transmission lines to be operated at higher temperatures, somewhere between 212 degrees Fahrenheit to 480 degrees Fahrenheit. That's 100 degrees C to 250 degrees C. And you can do that for long periods of time. So what's on our system? currently. As I think it was Dave, if I got the names right. Yeah, Dave. Dave was our speaker. You know, we do have a lot of traditional conductor on our system, copper, and we also have aluminum conductor, steel reinforced, ACSR. It's the oldest on our system, the copper, and it's been in use for many years, back to the 1900s. We've also got a lot of ACSR, and it's kind of, as Dave pointed out, it's an industry standby for sure. And it's actually that way, not only on our system, but in the region. The region in the Pacific Northwest and the West began to grow up about the same time. And while there's been lots of new construction, there is existing construction and system that we have to deal with. So what have we considered in terms of advanced conductors? We've actually used and installed aluminum conductor steel supported, ACSS, and of course CTS Global talked about that type of conductor. We've actually been using that for about the past 10 years, and I'm going to ask Eddie to explain where those installations are. But it's you know, in our view, it's good advanced conductor. They're designed again to operate continuously at temperatures up to 250 C, and it's got higher ampacity, as Dave did point out. It does require different attachments on the structures, and we've done that in several locations that I'll ask Eddie to talk about. In terms of cost, ACSS is about 1.2 to 1.5 times more expensive than ACSR, so that's always a consideration. One of the other significant considerations for us is how does it really fit into our system? For long distances where you need high temperature and you want to limit your sag and it's maybe a new installation, we agree that this type of advanced conductor with a composite core could likely be a conductor that we would use. In many cases, we don't have the primary achievement or the primary goal we're trying to achieve is not necessarily the highest thermal capacity with the lowest sag. And that is because sometimes we have much shorter distances that we have to go across through an existing system. So we don't necessarily need that, you know, so every decision is an individual decision around conductors. We do acknowledge that ACCC is another conductor that exists out there, and it's of course the conductor that CTC Global was talking about. In many cases, we just don't necessarily need that in an application. We've actually analyzed it, and in fact, in several situations, we've taken a close look at it. We considered ACCC for our Jackrabbit to Big Sky Meadow Village project. That was a 161 kV project that was upgraded. It was a 69 kV system first. We upgraded it to 161 kV. And we also considered it for Crooked Falls to 2 That was a 100 kV project up over Kings Hill. But in our analysis, we determined that the ACSS, the steel supported structure, actually did what we needed it to do. And in this case, the cost was a little bit lower. So what I would say about these conductors, generally speaking, is that these folks analyze the situations we have for opportunities for reconductoring, for new build, and special situations like was described, going over large distances across a mountaintop, for instance, over waterways. And we take a look at all the different conductors that are available. We do have to make those decisions in the context of our overall system. The other thing I'd like to mention is that in general, we're not a thermally limited transmission system. We are in some cases, but in many parts of our system, what limits the carrying capability on the lines is what we call stability. And that means that's how the existing transmission system interacts with the rest of the system and the interconnections around us to other transmission systems. In other words, there's actually more thermal carrying capability on our system than the interactive dynamic system will actually allow us to use. So those are some of the decisions that we have to make in terms of what conductor to use, what installation to place it in, how to design it. I guess I'd close my comments by saying that we believe that ACCC type conductor has a place on our system. at some point in time, probably in future applications where we've got long distances, high temperatures, high capacity that we want to utilize and also want to limit that sag. It also probably has some installation possibilities in specialized situations as well. But in general, I'd like to just make the commission aware that we do make these decisions on a case-by-case basis, project-by-project basis about what type of conductor to use. And we're committed to use the best conductor to do the type of things that the folks from CTC Global talked about. And that is make informed decisions for our customers, lower their costs, and also think about the future. What does the future hold in terms of capacity? Do we want to build capacity in? And as you're going to see as Eddie goes through some of these examples, we make those kind of decisions and we're building capacity into certain parts of our system as we go back and have to rebuild or build capacity in because a generator is interconnected to our system, or change the system out because we have to modify clearance considerations due to reliability criteria. It's not only about capacity, it's about capacity, reliability, compliance, and asset life. And we look at all of our capital investments based upon those 4 criteria: capacity, reliability, asset life, and compliance. So multi-decisional, multi-aspects made for all of our decisions. And obviously, when we do that, we are considering these advanced conductors. So with that, Eddie, do you want to go through the few items that we are actually working on today? And as I said, this goes back about 10 years ago. That's where a lot of that area is. Great Falls as well, Billings and Great Falls.
Thank you. Thanks, commissioners, for allowing me to be here today. As Mike mentioned, we have used this for a number of years, more of the ACSS type of conductor. We currently have it in Billings on a number of facilities. We also have it in Great Falls. We're currently building on the Monarch Kings Hill area, and we'll have a future project in the Butte area as well. The one handout that really has the images on the document, these are current projects that we have going on currently. Now, the first one is the Crooked Falls 2 dot line. This is a multi-phase project for us. And it's something that we did look at ACCC. I worked with Jeff and we did look at the conductor on this, just with the terrain, the type of structures we needed to rebuild. It just wasn't financially feasible to put that type of conductor on it. So we ended up going with the ACSS on this project. That's a lot of it. We can go into a lot more detail if you have questions on that, but we did review that on that particular project. This year, this will be our last year of this particular project. And we'll have a segment of that facility that will be upgraded to handle a lot of our current situation that we have on that facility. Granted, the whole facility will not be there because we do have the piece that goes to Great Falls and also over to 2 dot that will not have this type of conductor on there. That would be a pretty significant capital project for us that we need to look at somewhere in the future. But at least the rebuild portion is up to date for a new conductor. And you can see a lot of the structures that are on there. A lot of the rebuild is on steel. A lot of that was really put in there from a fire mitigation. Try to get rid of the timber in the wooded areas. If we do get a forest fire, at least we have some structures that can handle that type of forest fire. Second page, you can see the tight right of way. And a lot of these right of ways that do go with the forest, we are limited. And what that means for us is we do have to shorten our spans. We can't go long distances. With the long distance, obviously you've got a galloping issue or a blowout issue, I'll call it, that it's going to blow out. We'll picture someone jumping rope. All right, the longer you are, the bigger the loop's going to get. So we have to tighten that constraint up a little bit so we can meet obviously the clearances of the forest as well as to the ground. So that just gives you an image of the tight right of ways that we deal with. Second project that we have going on this year, and it'll take place. We have 3 phases on that. We had a segment last year up in Great Falls from the Great Falls 230 switchyard to Riverview then Riverview over to the northwest taps. Our phase one is complete from the 230 switch yard to Riverview. This has that high advanced conductor on there. And then this year we do have a small segment. We're going to be going from northwest to northwest tap. And then next year we will finish that up. So we do have this in the Great Falls area. We also have another facility in Great Falls that does have this type of conductor, and that is also from Great Falls 230 switch yard down to Montana Refining. And that was installed probably getting close to 10 years ago up in the Great Falls area. And you can see a lot of the pictures. I didn't have any great pictures of really the right of way per se of, I think the section that we did rebuild last year is obviously more wide open. We don't have a lot of more of an urban type setting up there. So the right of way is pretty wide open for this. We are able to use a lot of our existing structures with this type of conductor. So that is also a benefit, as well as CTC also mentioned on a lot of these rebuilds. So. And then the second picture just gives another visual of more of the structure changes. And one I wanted to point out with this last image here, as Mike mentioned, a lot of our facilities are, are 50, 60, sometimes are 100 years old. So whenever we do change this and put new conductor on these facilities, we have to upgrade them to current codes, guidelines, standards. And when we put new conductor on there and look at the new weather cases, a lot of these old facilities they can't handle it. So we do have to raise facilities, upgrade them, and those sorts of things. So on both of these projects, this second one, we did not consider the ACCC conductor for these ones. And the reason is for this is a lot of it, the first phase, I would say, is more out in the rural type, but the second phase of it is in more of an urban type area. So what does that mean for us? We got shorter spans. So more of a picket fence type versus something that maybe 600-800 feet, 1,000 feet long for spans. So the benefit of using ACCC was not there for us financially, or we didn't need the low sag. We could still put a CSS on the facility and still get what we needed for the facility. So that's why we did not, and we didn't want to use multiple types of conductor as well. Could we use it on something that is more wide open? Absolutely. But the next phase, it doesn't make sense to switch up conductors from our perspective. Same line, having two different types of conductors makes it confusing for crews and those sorts of things. So for this one in Great Falls, we did not consider that ACCC. You bet.
Yes, I just close our comments, Commissioner Pinochi, by saying that in the handout, the first one, we did include a table at the end that compared, at least from our perspective, a number of the different type of conductors from ACSR to ACSS, ACCC, and then there's another one that we talked about in here as well, and it was called C7, and we actually considered that for a project as well in the Helena Valley, and Tom can probably shed some light on that as well, because that's a fairly recent decision we made. Tom, if you want to say anything about that. Sorry about that.
Thank you, Mike and Eddie. Thank you, members of the commission. Yes, this is Tom Pankratz. I'm the Director of Transmission Engineering for Northwestern Energy. And I've been before the commission before. I would say that it's a pleasure to be here today to talk about a topic like this. It's very seldom that as engineers, we get a chance to talk about these types of topics that kind of get Eddie and I excited versus oftentimes other things we have to come before the commission on. What I would share with you is, as Mike said, is that I don't think there's anything within the CTC presentation that we would disagree with. Quite frankly, we agree with many parts of all of that. As Mike indicated, it's very challenging when we look at our system in terms of making decisions on what conductor gets put up in terms of projects as they come before us. It's true that we are an aged system, but we're also, in areas where we do find capacity constraints. We certainly consider advanced conductors in all of these cases. As you heard from CTC as well, I mean, when we look at conductors and starting to compare the various conductors, frankly, and you'll see this in our materials as well too. Today, our standard, we believe, is advanced conductors for any reconductor or new facilities, for example, that we would build today. The question then becomes around, some of the design considerations, as you heard today, about what core that you use within that conductor. That's, really from the engineering perspective, the things that we think about with that. And as you heard, CTC, of course, manufactures the core. The conductor, the current carrying component of all of that is, other vendors that produce all of that and, similar vendors that we all use today. I guess the last comment I would make in closing, I found with interest one of the terms that you heard today was future proofing. And as an example of some of the projects that Eddie shared with you that Northwestern has underway even as we speak, literally today in the Monarch area, where we're reconductoring our Great Falls to 200 kV line segment. And as an example, that's a line segment that's approximately 100 miles long. We are rebuilding the middle segment of that line, which was nearly 100 years old and in need of rebuild. So we're reconductoring the middle portion of that line, and it was more structural decisions and engineering reasons why we do that. But what we're doing with that is we're putting up an advanced conductor for that segment, and I'd like to use that same term. I think if I can coin that as well as future proofing, because while the existing line segment, I'll just use some rough numbers for you. Existing line segment capacity was about 42 MVA. Okay. With the new conductor we're putting up, that 100 kV line segment, we're prepping that line segment to be able to be good for approximately 210 MVA. Okay. So roughly 5 times the capacity that we'd be able to put through that one line segment. And as that future capacity need comes forward, that's when we would bring a project like that forward. So that's, in closing, that's what I would add. So thank you.
Should we take questions from the commissioner now? I'm sorry. You had closing
I'm
remarks.
just going to ask about the next step of the process. So whatever you'd
Questions
like,
from the commissioners. I want to encourage the listeners to know that you'll get a chance to ask questions if there are going to be any. So make it a good one. And one of the reasons I'm having the commissioners go first is they may ask a question that you would ask. Mr. Townley, I'd like to invite you to this chair here so that you could take a question or two and have a microphone. And so now I'll turn to Commissioner Fielder and Vice Chairman Johnson, and I'll follow up after they do.
Thank you, Mr. Chairman, Commissioner Pinocci, Chairman for the meeting. Thank you for the presentation, and thank you to Northwestern too for being here to provide more information. I think it's a really important discussion to have all the parties involved in. So thank you for your time and effort to everybody. Couple questions I had. This core, Mr. Townley, with the fiber, is that that's more resilient to heat than the older products that are out there?
Yes, Commissioner, substantially so. And it's often translated in what's called a coefficient of thermal expansion. As it heats up, it doesn't expand like the steel expands.
So I was wondering about wildfires and whether this is something that might withstand the heat of, I mean, obviously if there's a intense fire that, could take out a structure and melt the metal and that kind of thing, this probably wouldn't help. But when fire is in the vicinity, it can be very hot on, because the transmission lines are clear, but the trees are burning, 100 feet or 200 feet away and can add heat. Would this, is this something that would potentially make improvements in the resiliency of the grid to wildfires? Because I know we have a lot of wildfire risk.
Yes, and in 2 ways. So some of the traditional that's up is even as it gets up into 100C, 200 degrees Fahrenheit, it has to be replaced after the fire has gone through because it's now annealed. It will sag more heavily in the tower. It may now have clearance issues to the ground. So that's one approach. But the other is because it's so low sag and this class of conductor, and you can see that there's some differences among them, but as they heat up, and I showed the chart that showed some differences among how much they sag versus the heat. But here, the sag is low. You're staying very high above the undergrowth fire. And again, there are some fires that, you may bring it up higher, but generally a fire, fast moving fires through these areas. We have done our own testing. And so I can quote that we have tested sustained at 600 C before we see any kind of damage to this conductor that would cause us then to have to replace it rather than the resilience of coming back and immediately being able to continue operation.
Okay, thank you.
Mhm.
I have a couple other questions on different topics. Should I continue or did anyone?
Please continue.
The lower first cost you talked about, it sounds like I heard different information from Northwestern. They said they agreed with your presentation, but I thought I heard you say that the costs are actually lower for this type of material than the competing material.
One that is almost hands down, and again, I want to address a class, hands down would be if you're able to use the existing structures and not rebuild them, then you're going to have the lowest capital cost to upgrade those lines to the extent you can use any of these advanced conductors, certainly the ACCC. The ACCC happens to give you that opportunity to have the same diameter and the same weight as what you're going to take down. So the tower, the structures were designed for that size and weight. That gives you a special opportunity to be able to use those conductors. That is a low-cost solution. You may have to rebuild. If you're rebuilding, you'll bring other technologies in to compete then. Because once you start having to rebuild the towers, you're going to compete several things together then. But if you can use those towers, there's hardly anything that will be lower cost, I would posit.
You might need a different adapter, but for Northwestern staff, your chart that you gave us, am I reading this right? The grid on the last page, cost adder compared to the ACSR, you're saying that these ACCCs are 150 to 200% more expensive. Am I reading that right? Just the material, just the product?
Yes, I mean, and maybe we can, obviously the first cost that I think Dave is talking about there on a $1 per megawatt of capacity basis, and putting a advanced conductor on an existing system you can probably get a lower $1 per megawatt of capacity installation, higher cost overall. It might be a $10 million project compared to a $5 million project, but you added some capacity in, and that may be the right decision to make. And we've made those decisions, as Tom just described. We are using advanced conductor on a portion of line that it will have that advanced capacity. The two ends of the line on the other side of it won't have it yet, but maybe at some point we'll be able to do that. So I think you got to be careful to what's low cost. Low dollars versus low dollars per megawatts of capacity. And first costs are that investment. It's the raw dollars of costs. So you have to make sure you're talking about the same units there and dollars versus dollars of capacity.
Okay, thank
Agree with
you.
that.
Appreciate that clarification. Did you have something to add to that?
No, I say I would agree with that. And dollar per capacity, we would say that for reconductoring on existing structures, I don't think there's anything that would beat that.
Okay.
And to be clear, you'd get a benefit out of any of these advanced conductors, and comparing the conductors then is the right thing to do to see what capacity you get and what's the cost of that overall upgrade.
Okay. Another question then, I think this one for Northwestern, and that would be the subject of line loss. Commissioner Pinocci has brought this up with me, and if these don't lose as much voltage, for lack of the correct term, sorry, Mr. Engineers here, but I understand line loss in concept, and so the further it goes, the more the power dissipates, and the less you get coming through it. So I'm of the understanding that these have a greater savings in terms of not being subjected to the same amount of line loss. And so how is that a factor that you would consider, or is it important?
No, I think absolutely it can be a factor in your overall decision. So if you've made the decision that you have to replace a line, rebuild a line, whatever it might be, or build a new line, part of the benefit that can be had is what is that line loss? What's the efficiency of the conductor? And as Dave indicated on one of his slides, that was one of the components that brought in that particular case. It was as a piece of savings or a value added that helped that company make their decision.
Yeah. Okay. I had just one other thing, and I just needed a clarification on it. I wasn't understanding quite clearly. At first, the conversation from Mr. Cashel, you started out, I think, talking about how the high heat really wasn't that important because you weren't experiencing that. The capacity wasn't really that important. So,
let me see if maybe I can, what I was describing there is how our system interacts with the rest of the system and the transmission systems around it. And at times, the thermal capability of the conductor is not the limiting factor for the amount of power that we can move from one point to another. And that's referred to as stability limitations.
okay.
And for example, the conductor that we have in place on the 500 kV system that goes all the way across the state into the Bonneville Power Administration system, the limiting factor on that is not the thermal capacity of the conductor. It's really how that 500 kV system interacts with the region around it. So in some cases, for example, the 500 kV system, uprating that with a composite core conductor probably would not be useful until much of the rest of the system was built and upgraded as well. So I guess it just goes to the notion that all the decisions we have to make about conductors are multifaceted. You have to consider lots of different data points and input.
Thank you.
Vice Chairman Johnson, you're up.
Thank you, Commissioner Pinocci, and thank all of you for being here. I really appreciate that. You know, I just would point out for the record that the commission did seek and get passed 2 sessions ago a resolution by the legislature that encourages regulated utilities to seek out, evaluate, and where appropriate, deploy new and innovative technology. So this is all part of that, and it's great. You all can't decide to use a new technology that you don't know exists. I think that's a pretty safe assumption. And I think this has been very beneficial. Mr. Cashel, I want to direct this to you or your folks. We've had a lot of conversation around here about a looming regional shortfall in capacity, 750 megawatts, whatever. There's some discussion that y'all's entry into EIM might mitigate some of that, at least in the short term, as we move stuff around. And then who knows where we're going to be 5 years from now or 10 years from now in terms of new generation to provide that capacity. I certainly don't claim to have that crystal ball. So looking at that situation, are there scenarios where transmission capacity, assuming things are done to address the system stability question, would that then lead to situations where there is a bottleneck, if you will, with regard to transmission capacity? Or is once you get the interconnectivity set, you're ready to go to meet that projected regional shortfall? Or how does this all fit together in terms of system upgrades for transmission and stability? And how would that impact the need for deployment of some of these new technologies if you have to upgrade your transmission capacity in addition to your stability?
There's a lot in that question.
Yeah.
I'll try to unpack it in a couple of ways here. First of all, I think it's all part of the overall solution. Increasing the efficiency of the regional transmission system has to be done in order to meet the renewable energy goals of many of the states within the Pacific Northwest. It's a known fact that additional transmission or more efficient transmission is going to be necessary. In our particular case, and I'll go to your question on the EIM. The EIM is going to provide us with opportunities on a within our basis to transact with the market in the Pacific Northwest and California. That gives us an opportunity to hopefully buy lower cost energy in lieu of operating higher cost resources, not only in our system, but across the entire footprint. What that should do is allow us, because we're able to dispatch on a 5-minute basis now rather than the traditional 1 hour, it should allow us to be able to better balance our system. And also the theory is that you can utilize renewables in a more efficient manner. But it isn't capacity. You have to show that you are resource sufficient before you go into the EIM market. In fact, there's a test. You take the test every hour to see if you are sufficient enough to trade in the market for the next hour. If you're not, if you can't provide your own capacity, then you're blocked out of the market for that period of time. So it doesn't replace that capacity that we need. So the 750 megawatt shortfall is or whatever the number is, and I'm not John Hines and his crew, so I don't know the number specifically, but it won't provide us with that capacity. But I would say that, and by the way, you talked about, can you remove the stability limitations within the region? Probably not. This region is so large, generation is very, very distant from load, that'll always be a characteristic of this region, as opposed to some of the other systems which are more thermally limited, some of the systems back east, that sort of thing. So that stability limitation is probably always going to be with us, even with the new grid. Even though there may be some more distributed type generation, that limitation will probably always be inherent in the system. So I would say that any opportunity that we can take as transmission owners and operators and just prudent designers, we should build more efficient transmission capacity into the system. And again, on a case-by-case basis, we'll try to do that. But as usual, there's no silver bullet. It has to be done kind of incrementally and taking the opportunities from a generation capacity standpoint and a transmission capacity standpoint are important. We mentioned Billings. From a transmission capacity standpoint, Billings is one of our largest growing areas, and the transmission system into the Billings area, we're constantly trying to catch up with the load. That's why in that area, we do have and have used more of this advanced conductor. It's in the installations we've used it in, it's been more conducive to that. I don't know if I answered your question, but I tried.
Well, I think to begin with, you really did hit the nail on the head with the observation that there's no silver bullet. And it's going to continue, I would suspect, to be a moving target as we go forward. I've said ever since I've been here that anybody tells me they know exactly what the electricity sector looks like 10 years from now is kidding themselves, because I think there's all sorts of unanticipated stuff out there that we're going to have to deal with. As far as the 750 megawatt number, I guess we can agree that's close enough for government work at this point. So.
Close enough for an informational meeting.
There you go. Thank you. And Dave, you and I have had extensive conversations about this. I really don't have anything further for you other than, again, thank you for being here. I appreciate it. Commissioner Pinocci, thank you.
Thank you, Vice Chairman Johnson. Okay, I've got a lot of ground to cover. I should explain to the listeners and everyone involved that I've been given talks about this in other states and have certainly covered the travel on my own going to those other states. One of the reasons I've got such a great interest in this is I want everyone to understand that there is a National Committee on Electricity, and it is chaired by Ann Rendall out of Washington, and I sit on this board. I am trying to lead a country in efficiency because I sit on this board, and a good place to start is my own state. This is why I think I have a greater interest in this over the typical commissioner, because I sit on this national board. So I want to explain that that's one of my great interests, trying to improve the efficiency of the grid in the United States as a whole. What has happened in Texas a few months ago was quite serious. Over 100 people are dead. Every commissioner has resigned. I'm sure each commissioner, if they could turn back the clock, would have had all kinds of ideas to prevent what happened. Also, a few months ago, Northwest Energy let me know that they do not have enough electricity to supply, and they had to go to the open market. And they were quite concerned they wouldn't get it, but by some miracle, power lines went down in Oregon, and the energy supplier was able to provide electricity to Montana at 5 times what we normally pay. And I really am behind Northwest Energy producing more power than what is needed, and they could then sell their power to the open market so that we do not rely on working with others to provide us energy and hope that we're going to get it. One of the ways I think we can do this is if we can cut the line loss, I believe that we'll meet that goal a little quicker. Given talks, most people have no idea what line loss is or what a conductor is. So I'd like to explain to you how I explain it when I'm talking to a group of people that don't know. When you're watering flowers and you look at your garden hose and it's leaking water from several holes in the hose and your parking lot's getting full of water, if I could go tape 1/3 of those holes, I would be more efficient. I wouldn't leak that water out. That is exactly what electricity does, and the ACCC says they can cut that line loss by 1/3. So people understand that, and a conductor is the actual power lines. Now, I've been visiting with some linemen who are retired from Northwest Energy, some who, I think at least one who currently works there. And a question I have for Northwest Energy, is it true that in most cases, when we replace line to new line, it is the old technology steel core? Is it, we are not at a point where most of the time we're advancing to the more advanced conductor? In most cases, we're still using the old technology. Would someone like to answer that? Is that true or false? This includes lines going to someone's home or restaurant, not just the high capacity lines.
Yeah, thank you, Commissioner Pinocci. I would say in general, and I think as we put in our document, from a transmission perspective, we have changed our standard to be more of a advanced conductor. So I would say that's not true from a transmission perspective within the last several years. Overall, as you point out, asking the question about lines to home, service lines, distribution lines, et cetera, it's true that in general, for our distribution facilities, for example, or service lines are generally still a typical, more standard aluminum conductor.
When listening to the ratepayer across the state, some things they point out is we feel that every time a line is replaced, it should be the highest performance line, thus saving this waste, the leaking water falling out of the garden hose. Why in the world wouldn't we do that? An answer I'm hearing is a possibility is there's no incentive for the power company to move to the most efficient line because your profits are guaranteed. But yet the ratepayer says if we could move to the most efficient line, rates would have to come down over time. These lines would be paid for quite quickly, according to testimony from Dave Townley. One thing I heard mentioned is capacity, reliability, asset life. The ACCC and the performance of these lines even exceed things that were mentioned today. And I'll tell you some things that are talked about in some of my meetings that aren't talked about here today. I bring up a solar flare like the Carrington event or the use of an EMP weapon from the enemy. And I've been criticized that I shouldn't go there. Yet the federal government has reminded me that is one of the third most important concerns that face the grid. And we've lost a large portion of the grid due to an event similar to that. And this line is going to be better prepared to handle that event because one of the things that happened during that event is sag. The steel core under that heat and conditions will sag. And that's a big reason that the line will have to be replaced, costing millions, where this line, the high performance line, might have a tremendous amount of survivability and not need to be replaced. The concern that the grid is EMP or solar flare resistant is a very important issue. And the ratepayers want to see every line replaced to the line that's going to have the greatest amount of reliability in these severe conditions. Also, the ratepayer recognizes, and I didn't hear it mentioned today, that these high performance lines cut fire mitigation in half. Look, if in California, an entire power company went broke and it cost $1 billion, if these lines were installed, we could have cut that to $500 million. You're talking about saving millions and millions of dollars of fire resources. Every time the fire department has to go out, that costs the ratepayer money. That savings to go to that power line is saving money to the fire department. I have actually spoke to fire departments, one fire department about this. They're very excited about endorsing this because it could cut their calls in Montana in half. And with the forest and the dead pine beetle and the very difficult conditions we're in front of, this power line or a performance power line that cuts fires by half would be millions of dollars of savings. I don't see that that was mentioned today, and I think it's worth talking about. The ratepayers asking these questions, and I certainly wanted to bring that up. Line loss, the ratepayer believes that they'll have a lower rate. Is it true that Northwest Energy, and I'm not asking this to put you in a difficult position, maybe we need to go to the legislature and say, because you have a fixed profit and there's no encouragement for you to move to a high performance line, we see incentives for wind and solar through subsidies. Why in the world wouldn't we have something like that for a line that produces a savings 24 hours a day, 7 days a week, protects us against fire? It seems that that would have a higher importance than subsidizing wind or solar. There's a lot of questions there, but how do you feel about that as Northwest Energy? What incentive would you need to make it so every line that's being replaced would be the best performance line on the market? What are your thoughts there?
Well, as you said, Commissioner Pinochi, there was a lot there. So I guess I'll try to address what I think was your core question, and that is, should there be a wholesale move to, in all cases, an advanced type of conductor? And I think it was maybe even the type of conductor with the composite core. And going back to what I believe is the way we prudently manage and design our system is we'll go to the best conductor and from a standpoint of value to the customer for either capacity, reliability, asset life, or compliance requirements for each situation. And that, in our view, our professional prudent review, that doesn't necessarily mean that you would have the entire system transformed to that type of conductor. Certainly, when you have the opportunity to change conductors, upgrade systems, that gives us an opportunity, I think, to invest in conductors that do all the kind of things we've been talking about today. But I believe that each instance is is a separate, unique decision, and that the best decision from a consumer standpoint may not necessarily be the advanced conductor, but when we have the opportunity to use an advanced conductor, realize the savings associated with line losses, that's what we ought to do. Just kind of for information, I guess, to give you an idea how the efficiency of our system has improved over, the last handful of, well, I'll call it a decade, maybe two. When we did our last FERC rate case, which was back in 2006, we did a study of the line losses on our transmission system. And you do that in order to set your losses for rate making purposes, because losses exist. They do exist on a system, and you have to recover those losses as part of your rate making process. So back in 2006, when we did a study of what our actual losses were, we came up with a value of about 4% was our transmission loss value on average over an entire year. It was about a 4% number. So we filed a rate filing at FERC and the Montana Commission in 2018 and then 19 respectively, 2018 for Montana and 2019 for FERC. Did another line loss study, and our losses had dropped to 2.16%. Sorry, it might be 2.6. So a significant loss, a drop in our losses over that period of time, mainly because we've been aggressively upgrading the system through all of our different initiatives, including our transmission system upgrade initiatives, our substation initiative to upgrade the systems. And every opportunity we get to invest in new systems, they're just for one reason or another, well, just because of the age, they are more efficient. So we are realizing better losses across our system, and every opportunity to invest in an advanced conductor will help that.
Thank you for that answer. About a year ago, maybe more, I put a couple people to work on studying your line loss that was posted on the website. And I was quite proud of Northwest Energy because the line loss seemed to be actually outstanding. But I was told by some individuals that it wasn't realistic. The line loss had to be more than what was posted. And I believe I took the concern to Dave Townley, and Mr. Townley, you looked into it, and I see you were taking some notes. What was the results of that meeting? Was it unrealistic, and we were going to try to work with Northwest Energy to understand those numbers? What do you remember?
I'm sorry, I don't remember that conversation.
All right, well, that's something I wanted to get accomplished. It looked like
that looked like that was an issue I wanted to double check into. And again, the numbers look really, really good, but a couple of individuals thought that it was unrealistic because other power providers in the country couldn't have numbers that good.
So on our, Commissioner, to your point, on our transmission system, those are the calculated losses that we came up with our rate filing, and then we supported that within both at Montana, at this commission, and at FERC. And we recover in our rates for losses based upon that. So if our losses were significantly greater, we would be under recovering our costs. So we stand by those numbers, and that's what we are getting recovered in terms of the overall rate. So I feel good about the numbers, and especially how they came down over about a 50% reduction over call it a 18 or 19 year period. And that's primarily because of the equipment that we've taken out of service and put back into service.
Chairman Ann Rendall in Washington, I want to get a recording of this hearing to her quickly because the transmission lines from Colstrip go to Washington. And I see the opportunity where if we were to upgrade those lines, that we could do so under maintenance without a permitting process and nearly double the capacity. Now, one of the things I had mentioned in Northwest Energy over the past couple of years is if they get a greater share of Colstrip, this I was hoping that a greater share of the power lines would go with it, and we could then send wind and solar to Washington. We then could cut the line loss by a third and increase capacity, thus giving Washington that needed energy. Energy is going to increase. There's no question about it. The country is growing, and the growth of electric cars is going to be phenomenal. And I just see a great future for Northwest Energy. And one of the things that's just incredibly got great potential is these power lines that go from Colstrip to Washington. And with this technology, we can upgrade this. And Chairman Ann Rendell has to really look at that as an opportunity to get power to the Seattle area, which then can be transferred to Oregon or even California. So I think that Montana has this tremendous potential to grow and have this advantage by this power line upgrade. This also came up in Sydney, where they have a coal fire facility in Sydney, and the talk of increasing the power at the facility was quickly just given up on because of the restrictions on the capability of the power lines. Nobody brought up the fact that under maintenance, we could move to the ACCC and nearly double the capacity. And I tried to bring that out, but no one really, I think, believed it. A few months ago, we had a meeting with Northwest Energy where the day we were talking, it was really high winds and power lines were coming down. And I had brought up, hey, the ACCC handles itself much better in high wind conditions. An answer I got back from Northwest Energy is the ACCC only works with direct current DC. Might have been a misunderstanding, and there's no advantage to use with the smaller lines to a home or a business. Mr. Townley, what's your thoughts on that? Because one of the reasons I requested this meeting is to get some of these facts cleared up. The ACCC certainly does work on AC or DC, and there's advantages taking it to a home or business, not just high power lines. Could you shed a little light on that, sir?
Yes, I'll try to address some of those questions then. So AC versus DC, absolutely, it doesn't matter. It's a power line, and I know I wouldn't think they would draw a difference between an AC DC line. So maybe a misunderstanding in communication is a potential there. In terms of advanced conductors for delivery to homes or businesses, advanced conductor sizes aren't down into the low voltage distribution. They're moving into the upper voltage distribution now. Several products are being developed. Certainly CTC is developing, some others will be developing products that move into that upper voltage of the distribution lines. And that's an area, again, rules of thumb is your distribution is twice the losses as your transmission systems are. So there's opportunity there, but we've got to get products to be designed and move into that area.
Is it true that if we could move into the residential area, keep in mind the Public Service Commission gets complaints when there's no power. That's when the phone calls start rolling in. Would we be able to see less calls and a more reliable system due to high winds if everything was ACCC? Or your thoughts are going to residential and small businesses, it's not a good fit. What are your thoughts there? The ratepayers asking these questions.
Right.
I said I would bring that question out.
Okay. I would probably recommend now to stay out of the discussion of residential and commercial. It's probably a ways away, bringing those lines down because you got to design the line competing. But as you move just above that into 12 to 20 kV, and then up from there into the mid voltages, 30s and 60s. Yeah, there's real opportunities. And because they're low sag, you are correct to say there's less blowout. And I think the comment a little earlier. So there's less blowout. You can get more benefit in a constrained corridor and be able to upgrade that corridor without having blowout effects of a line that might sag more.
Well, thank you. Commissioner Fielder, any questions? I'd like to turn it over to callers that are on the phone that have been waiting. Oh, I'm sorry.
Yeah, before we go just straight there, I'd like one comment, and well, I've got Commissioner Fielder still here too, because I want to follow up on a comment that you made. The presentation you heard from Northwestern Energy, this is their home. This is the system they're defending. They have to make you comfortable that they know what they're doing and that they are doing the right thing, looking at new products, right? And we want to bring the information, we're working with them as well, for those new products, how to apply them for sure. But we heard 4 design criteria, and Mike repeated them at least 3 times now for the 4 design criteria that they use when they're deciding. And though he commented about energy efficiency improvement and the need for efficiency improvement, I just want to highlight that energy efficiency was not one of those design criteria. And that was one of the proposals that we were making to you. You can get great energy efficiency improvements, and we've seen it all across the country as systems have been replaced and upgraded. But that's often an after the fact view of how well did we do? How did we increase? I'm encouraging, welcome the response, but encouraging that energy efficiency be explicitly added to that design package so that as they're designing, making those trades, one of the pieces is not being left off the table. The benefits flowing to consumers for lower energy costs, lower line losses, that's also explicitly included, and that they can expect if they include that and they make those trades and they're bringing those packages to you, they're not going to be second guessed. They're following procedures that you can lay in place that says, no, that's the right decision for the consumer, for the environment, if you're following this process.
I appreciate the opportunity to respond to that because I didn't mean to imply that energy efficiency isn't considered, because it certainly is. There's 4 major criteria for us determining if we have to make an upgrade to the system. That's capacity, reliability, asset life, or compliance reasons.
Right.
In all of those cases, part of the decision in design making is always efficiency and what's the best conductor in speaking of conductors. So don't misunderstand. I mean, it's always a major part of a decision that we make. But the 4 drivers for having to make a capacity capital investment on our system remain those 4. Asset life, things wear out, right?
Right.
Reliability, we have to be able to deliver when we need to be able to deliver. Capacity, we have to have enough capacity to deliver to our customers at all times. And then compliance, there are certain rules around how we deliver. So those are the 4 drivers, but embedded within that is energy efficiency and making the right decision around the assets.
This is great dialogue. I'm glad both parties are here.
Mr. Chairman, I have a question.
Commissioner Fielder, yes.
Thank you. How are those 4 criteria determined? Are those self-imposed policy criteria, or is that within your division, your engineering division?
That's a great question. Not self-imposed necessarily. There are criteria at the NERC and WEC level, and in South Dakota at the SPP level, that we have to have a certain amount of reliability. We have to meet reliability criteria from a transmission planning standpoint. There's dozens and dozens of standards that we have to meet that are not only standards, but they're also criteria you must meet with, and there's a possibility for civil penalty if you do not. So they are, there's also the National Electric Code, the NEC. There are lots of rules that we must live by. And then we have our own standards as well. We have our own self-imposed standards. And I'm speaking primarily from the transmission and distribution standpoint. So again, all those things are reliability criteria, asset life. There are standards around the industry about how long a piece of equipment, how much life you should get out of a piece of equipment. And then there's the reliability criteria that is sanctionable and enforceable by NERC all the way up to FERC.
I have one other question, I think, and that is, and you might not be able to answer this. This might be more of your fiscal folks, but my basic understanding is that when Northwestern invests in a capital improvement project, a capital project, an upgrade, that statute right now requires that the ratepayers pay 90% of the cost and then the company pays 10% of the cost. Is that correct?
Well, I think what you may be referring to, and we may have to take this offline to someone who can help you with your question, but I think that's really the power cost adjustment mechanism, the 90-10 sharing and that. And perhaps Shannon, you're still here.
Is that more for acquisition than for?
Lost our attorney. But that's something we can take back. But there is no 90 and 10 sharing on capital projects. The way we recover our costs from T&D capital standpoint is to do periodic rate filings.
Okay, I think I do have that confused with the capital acquisitions statute. But okay, here's the other one in revenue requirements. And when we calculate those, Mr. Rosquist is here. Good. Will, you might have to answer this. The company, invests in these upgrades and things, and those are part of the cost of doing business. And so the company gets to recover those costs, plus I think some kind of a return on investment percentage. Is that right, Will? Okay, he's nodding his head yes. Okay, so there's not you feel free to come up and answer that if you like. What I'm getting at is there an incentive to provide for these types of upgrades, just as there is for putting in the smart meters or any other improvements that the company's making? There's that return on investment that the company can recover. Is that right?
Well, Commissioner Fielder, yes, this is Will Rosquist, Regulatory Division Administrator. And you are correct that when the company makes, and I'll weave this into Mike Cashell's answer as well. So the company's making ongoing investments, capital investments in their transmission and distribution system. They will add those investments to their rate base. They'll come to the commission at a rate case. At that time, the commission will look at the rate base at that time and the accumulated depreciation that's on their books at that time and reset rates at that time. And as part of development of the revenue requirement, you're also correct that there will be a rate of return that gets applied to the rate base in the development of the revenue requirement, and the rate of return, at least in theory, provides some incentive for the utility to make the capital investments that are necessary to provide adequate service to the customers.
Okay, so there is a profit incentive for making improvements. So there's not a disincentive for the company to not do this kind of thing, correct?
No, I think you're correct, Commissioner Fielder, that, and in fact, to some extent, someone might be able to argue that to the extent that the advanced conductor is a greater first dollar investment, that there's maybe even an incentive to choose that over a cheaper incentive or a cheaper first cost investment to the extent that they earn a return on it. Not saying that that's what Northwestern would do, but that's where the whole gold plating theory comes into play, that you might want to prefer, if you're a utility that's motivated by profit, prefer a higher investment option.
Thank you. I just want to say I like what I'm seeing with the product and its benefits, and it seems like it could be beneficial to not only the consumers of Montana and help stand up to wildfires and that kind of thing, but maybe extra beneficial to the company as well. So I hope you'll have those internal discussions about the finances involved in it that go beyond maybe typical analysis.
I'm sorry, I couldn't quite hear your last comment. I'm sorry.
Oh, I said I like the product and I hope you'll have those internal discussions about the fiscal aspects of it that go beyond your engineering calculations in terms of rate of return, revenue requirements, the benefit on, the return on investment that's provided when you do something like this. I think it may help your company's profit margins. At the same time, it helps the consumer and it helps capacity and it helps provide, prevent line loss and that type of thing. So more power is getting where it needs to be with less generating costs and that kind of thing. So I don't know. I think this is a really neat, innovative product. And I'm my mind is thinking about what's next. What's the next generation of this? Are we going to make them for underground? What's coming in the future? But
More efficient materials.
yeah, we go to the moon and do a little mining there, maybe.
Who knows?
Well, thank you, Commissioner Pinocci, for holding this. I really did enjoy the information that I obtained and the information that was provided by Northwestern and CTC Global. Thank you.
Thank you. The commission now invites members of the public to pose any questions raised by the presentation to Mr. Townley or Mr. Townsend or Northwest Energy. Likewise, if there's any members of the public who would like to make a general comment, they may do so at this time. When you make your comment, please come forward, speak into the microphone. Please also state your name and where you're from. Is there anyone here? Yes, sir. Go to the microphone.
Thank you, Commissioner Pinocci. For the record, my name is Drew Zinecker, Zinecker. I am a resident of Lewis and Clark County, and I want to say that very few people keep me thinking more than you, Commissioner Pinocci, and back to your days in the Senate, very few people keep me thinking as hard as you, Commissioner Fielder. And before I read my prepared comments, I just have to say that your opening questions made me think of something as Northwestern responded to one of them and talked about how different power systems and providers connect. I look back to the example of someone who grew up in a broadcasting family at transmitter sites when all of the TV stations were forced to go digital. And all of a sudden, when everybody had to do that, when government did give the private sector a little kick, which I'm not always the biggest fan of, as I know you aren't as well, the industry really stepped up. And I saw buildings that were full of equipment for just one station, all of a sudden basically empty. A cooling magnet called a klystron that weighed thousands of pounds go down to something that weighed 30 pounds and no longer required an enormous tank that filled up a room from floor to ceiling to cool the magnet. So I think that as we challenge people with products like this, that hopefully the whole industry will step up. So to my prepared comments, the ACCC Conductor from CTC Global, an American company, is not conceptual, it is proven. It has been proven in every market around the globe where it has been used. With Montanans not being served by 21st century utility infrastructure, we will continue to fall behind the nation and other states and the world in which we expect our businesses and residents to compete. If we take the necessary steps to utilize this terrific product, not only will we see a rapid financial return on this critical infrastructure investment, but it will better provide Montanans with the utility service they rely on, they expect, and they pay for. I will never forget during this last legislative session, waking up to a text message, which it was just a few months ago, from a legislator asking me to help find information about rolling blackouts in his constituents' homes. They were contacted by the utility with less than an hour's notice, letting them know that with no definitive date or time end, they would be facing continuing rolling blackouts. And I thought that day, February 16th, 2021, put elected officials, the commission, and utilities across our state on notice. While the rolling blackouts I'm referencing affected utility ratepayers in a cooperative, which is not regulated by this commission, Northwestern Energy warned us of this very scenario in this very room and on that very screen right there when they presented their IRP before the commission and the public. Such a capacity crisis, which affected markets across the nation, led to the death of at least 111 people in Texas and led to the resignation of the state's entire Public Service Commission. Those 111 lives could have easily been lives in Macomb County, in Sanders County, or in Lewis and Clark County. And those commissioners who resigned very well could have been the 5 people that sit up here had the regulatory structure the legislature put in place been different on that day. If Montana and the entire nation had the ACCC conductor in use during capacity shortages, utilities and governments would be able to say they are trying their best to prevent outages caused by capacity shortages. With a volatile open market, unstable natural gas prices, failing intermittent power, and litigation contributing to an imbalance in our state's energy portfolio, we cannot afford to delay investment in this product. Texas has proven that meeting consumer demand is literally a matter of life or death, and it is possible that we may learn that in Montana next. And I'll just end by acknowledging that this proven power conductor represents the most significant advancement in utility service since the first light bulb in Montana was installed at the Alice Mine in November of 1880, which is about a year after Thomas Edison invented his electric light. Thank you.
Thank you, sir. Any other public comment within the room? All right, let's see if we can get a caller. Do we have any? Okay, well, I did to Matt.
So I'm not sure if you still want to talk.
Do they have the ability to raise their hand on screen?
You have to unmute. I think you click on ask to unmute, hover over that. This is the group.
Would you like to make a comment? Can you hear me?
Yes, I can. If it's directed at me, this is Matthew Hutchison. I'm the Vice President of CTC, and I've been listening to this for a little bit. And very well job, well done, good questions. Northwest Energy, myself, I called on you guys in my early years with CTC. I would ask you, commissioners, to get a hold of Mark Gabriel, the old CEO of WAPA, who presented at the Seagray conference I attended, wildfire presentation on the car fire. And in that car fire, a lot of things happened, as we know. But 58% of all the conductors that weren't even directly in the fire, but came in close contact, had to be replaced because it became annealed. Okay, that means it sagged. Some of it sagged and caused secondary fires, but all had to be replaced. Even conductor that didn't show any damage. As you know, ACCC is already annealed, does not become annealed in a fire. It sags almost 27% better than ACSR. And you reconductor on the existing structure. So there isn't really any gold plating when you go to an ACCC conductor versus a steel core or any other conductor, because you're still going to use the same structures. But the one thing you have to be aware of with steel core, and I'm sure the fellows from Northwestern Energy know, that there is a zinc coating on the steel that protects the steel from aluminum galvanic corrosion. At a very low temperature, that zinc goes away. So even though the conductor doesn't look damaged, it will start the galvanic corrosion process. So again, with a carbon fiberglass covered core, you do never get a galvanic corrosion between two dissimilar metals. So that 58% of that conductor was, I think the numbers in the hundreds of millions of dollars to replace that would not have to have been replaced, is what I'm saying. So you want to take this into consideration when you look at the value proposition of ACCC as well, if that makes sense.
Thank you for that comment. And I see I have more to learn. about conductors. I did not realize that. That would be a very good point to bring out today. I have to ask Dave Townley this. Are you familiar with the high performance conductor Northwest Energy is claiming they're using?
Yes, generally, and I would refer to my colleague who has quite a bit of information on it as well. Yes.
Well, my question to your colleague would be this. Did they make the right choice or should they change to the ACCC? I need to give you the opportunity to see what your thoughts are on that.
This is Jeff Townsend. I'm a director of strategic accounts. I've been calling on Northwestern Energy since 2010. I'm a Montana native. Great question. Southwire C7 is a composite core conductor. It is in the classification of high temperature, low sag conductor, as is ACSS, as is ACCR from 3M and ACCC. Those are all of the classified high temperature, low sag conductors. Southwire and CTC's products are the only carbon core composite conductor technologies. The main difference between Southwire C7 and ACCC is ACCC has a solid rod configuration of the core, and Southwire C7 uses 7 smaller individual strands. But it is still, you'll still see mainly the same benefits of almost no thermal sag due to its carbon core conductor technology. So it's really just a different format of the same kind of technology. So you get many of the same benefits, although their standard product offering at Southwire is a round wire configuration. So their standard product offering would not have the multiples of aluminum advantage that you get with the trapezoidal wire, but they do have a trapezoidal wire format as well. Does that answer it?
Well, let's get to the meat and potato. Is your power line better, or you say they're about equal? Maybe line losses, they're different.
We're priced lower than C7 for the projects we've worked where we're made aware of the pricing, such as a municipality when they post the bid tabulations. So we are less expensive than Southwire C7, and we have more casing mills per size for our varieties of conductor size offerings. And moreover, Southwire C7 is relatively new product offering. It's only been around for maybe 5 years or so. And ACCC has been around since 2004 and fully commercialized in 2005. And so as far as any of the high temperature, low sag composite core conductors, ACCC is far and away the most widely used technology with the most proven track record. I would say it like that.
Well, a fair question for Northwest Energy. Maybe perhaps the power line you have outperforms the ACCC.
So I think there's some confusion about this C7 conductor. We've never used it. It's simply a conductor was on our comparison sheet. The conductor that we've used is the ACSS. That's the steel supported conductor. So we've never used C7. We just simply included that on this list as another comparison comparable to ACCC.
So the lineman was correct in telling me that Northwest Energy has not installed any of the carbon core performance.
Oh, the carbon. That's true. We haven't. The advanced conductor we've used is the ACSS.
Is the line loss a third less than the standard? Is line loss not a factor with the power line you've been using? The ratepayer is very excited about saving a third in line loss, fixing the leaks in the garden hose, so to speak.
Yeah. So I could have Eddie or Tom address what the line losses are with the ACSS, but I guess I need to stress a point here that we will move to advanced conductors as it makes sense. But I get the sense that there's a suggestion to change everything to advanced conductors on the entire system, and that certainly does not make sense for any of our ratepayers now. There's a useful life for the system that we have, and as we get an opportunity to change our existing system out to more advanced conductors, and driven by another reason, that makes total sense to be able to move in that direction. But I kind of get the sense that there's a suggestion that you should just go reconductor the entire system, and that certainly doesn't make sense from a consumer standpoint. Changing the system over time, and I have the nodding of the heads going on here from the CTC Global folks, that I think that's what you would suggest too, that it's an incremental approach. And as you have the opportunity to upgrade the system, you look at these more advanced conductors. It doesn't make sense to do a wholesale change. Is that a fair?
So Dave Townley mentioned that, residential and business use didn't make sense to make that change. So they did say that today, and the ratepayer wanted me to ask that question. I just think this is great. We're all together.
I think this has been a great exchange, and that as the systems change over time, then there's going to be more conductors, more materials that emerge that make systems more efficient.
Mr. Chairman, I have a question too. Just to clarify, do you agree, Mike, that the wildfire resiliency factor is superior with this carbon core than it is with the other product that you're using, the other advanced system? Oh, here we go.
There you go, Tom.
Actually, I don't know if I want to touch that one.
Mr. Pancratz.
Commissioner Fielder, I guess how I would respond to that is, while again, with, very much due respect to, our friends here at CTC Global, first of all, I probably couldn't really respond in a real factual manner to that, but, from an industry perspective and the things that we see, there's some indication that yes, there's with some of the fires that have occurred even recently out, West Coast and California and different things like that. I've seen various reports where they've seen, yes, some of these are more resilient. I've also frankly seen reports where, these fires get so hot. I'll just tell you quite frankly, I don't care what you put up there. In some cases, we're going to have trouble in still replacing a lot of conductor, whether it's this conductor or an old standard conductor. I would have concerns to try to make the assertion that, hey, this one's just way going to be better in a fire situation. Quite frankly, I'd tell you, I don't think we know that for a fact.
Yeah, I understand. I mean, I have a 500 kV line on my property, and, it's cleared underneath, I think 200 feet wide. The trees next to it are well managed, unlike most of the Forest Service property, where they're overgrown and thick and have a lot higher intensity fire that burns through a lot of that untended national forest. But the reason I'm really keen on this is the very first time I was in this room before the commission was August 27th, 2013. And the reason I remember that date is because that was the day the United States Department of Agriculture was here with their full entourage, telling the commission, we have a big problem. We have 10,000 miles of major transmission lines in the West that are at risk on National Forest System lands from lack of vegetation management, primarily from the fire risk associated with that. And I brought the report up. I found it in my old records. And in Montana, it was 997 miles. And this is transmission lines, not distribution lines. So I can't even imagine how many more miles there would be in distribution lines. So I think this is another important topic to bring up is are these things more resilient? And yes, in a superheated situation, probably nothing's going to hold up. But in other situations where the fire is near and close, like I talked about earlier, is there a significant difference in the ability of this to withstand that type of heat versus something else? Because as you know, when power goes out during a fire, then you can't pump water and that type of thing. So, I mean, it's really critical to have that power if you can have it during a fire, if fire's near or threatening.
And vegetation management is key.
Spent my life working on that. Yeah. Trying to get that turned around. So yes, I agree. And it is a problem that it's not being managed quite that well on most federal lands yet. We're doing pretty good on private and state lands, but I would suggest that as you're looking at whether these are feasible or most desirable, you should get a copy of this report It was called Western Utilities and Forest Health by the USDA, presented to Montana Public Service Commission August 27th, 2013. And interestingly enough, the cover of their report, which was called Western Utilities and Forest Health, had a picture of a raging fire encompassing a transmission line. But that I would think that would be another important factor, is where you've got transmission lines crossing national forest lands, especially where they're not able to get in and tend it quite as well as some other areas. That may be a really important consideration.
Very briefly on that. Since 2013, actually, going back at least 5 years now, we've been actually working very closely with the Forest Service on that very topic. And we've been doing vegetation management and use data that they've got about the conditions in the forest and the bug conditions and so forth, and overlaid those conditions on top of our transmission lines, and then use that to prioritize where we go for transmission vegetation management, both inside and outside of the right of way. So we've developed a pretty good partnership with the Forest Service for those very reasons.
Good, thank you.
Along those lines, I believe I was told at NARU that the state of California is requiring the ACCC to be the replacement line after the $1 billion fire insurance claim. Did the insurance company require that, or the state? Does CTC have an answer to that?
Yeah, unless Matt can address differently, but I believe I'm not aware that requirement has been made. We are aware that SCE, Southern California Edison, in its choice, is replacing its lines, many of which were sag constrained or clearance restricted, and they're replacing all of those with the ACCC, and recognizing, although they will be quick to tell you, we do not buy this for fire mitigation. This is not a fire mitigation. But anecdotally, fire blew through. This came down and had to be reconductored. This we could turn on and keep running in that particular fire. So it is a probabilistic piece. There's going to be fires that come through that this is superior. There may be some that come through that nothing survives. So
When conversation possibility was brought up that an insurance company could start requiring it or have higher rates for those power companies that do not have sag resistant lines, is it CTC Global's position that fire is cut by half using this power line?
I don't think we would have the evidence to put a number like that on it, but anecdotal evidence tells you that it's more resilient. And I think, and the insurance companies are known for their very analytical approaches in order to make some money. Did really want to know, and I think we've still got a lot of data to collect to see what that translates to. Is it half? Is it 25%? Is it 70% survival? We just don't have enough data yet.
Thank you. Is there anyone else that would like to make a comment or say anything before I close the hearing? Anyone?
I just want to thank you, Commissioner Pinocci, for arranging for this, and I think this is a great dialogue. I think we're all in this together on assuring that we have the best conductors for the best application, and this was a good informational meeting.
Well, thanks for coming. I can tell you that Northwest Energy is extremely important to me, and to improve the performance any way I can helps Montana ratepayers, and I want to do everything I can to prevent what happened in Texas to happen here. Thank you for your comments and questions. This informational meeting is now adjourned.
Thank you, Commissioner. Right?